In this video, I'm going to discuss the idea of sign extension, and I'm using ARMv assembly using the GNU assembler. So down here, I've already created some data. So this will be the value of 20 stored in a word, which is 4 bytes. This will be -3 stored in 4 bytes. This will be 20 stored in a single byte, and -3 stored in a single byte. And what I want to do is add 20 to -3 in both cases. So I'm going to load register 1, comma, W positive. Now in this case, what I'm going to do is I'm going to take the address stored in R1 and override it with the value at R1. I wouldn't do this if for example, this was a value in an array and I was trying to move through the array. But here I don't care about keeping that. So R2, 2, 2, this will be negative. And then I will add those together. So add R1, R1, R2, which says add R1 and R2 together and replace R1 with that sum. And let's do the same thing now for those bytes. So now I need to add the part about a byte here, and I'm going to call this R3, 3, 3, 3, 3, R4. So the point of this is to make sure I only load a byte at that address instead of 4 bytes. And let's see what happens in the two cases. So now I'm going to assemble with debugging information so we can look at the debugger. So step, there's my 20. But what happened here? Isn't that supposed to be -3? Let's look at a moment at what's going on. So modern computers represent negative numbers in 2's complement, at least in general. So what happens? So I have my +3, which would have a bit pattern, say if we only looked at 4 bits of this right here. But I want to represent in the 2's complement representation for negative. So to do that, what I'm going to do is I'm going to flip the bits and then add 1. And this right here would be 8 plus 4 plus 1 is 13 in base 10, but in base 16, that is D. So what we have is, since I have 32 bits total, I have, remember I'd have leading zeros here for this, 0, 0, 0, dot, 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 0, and then 0, 0, 1, 1. And in 2's complement, then that becomes 1, 1, 1, dot, 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 1, 1, 1, 0, 1. And so 4 ones will be an F. So ultimately what I have is F, F for the top byte, F, F the second byte, F, F the third byte, and then F, because these are 4 ones, F, D for the last byte. And so once again, that is -3. And so we see that right here. Top byte, second byte, third byte, the last byte. So that is correct. And we can see that then when we continue to step, and now we add those. And we can see right here, I actually went a little bit farther, but we see right here that 20 plus -3 gave me +17. So now I'm in the byte section. So I load in the byte containing 20. Now we get the byte for the next part. And we set FD, but this is just FD, it's not all this. But the reason for that is that here I have a byte representing -3. So that is correct in 8 bits. But let's see what happens when we add. Well, I get a decimal value of 273. So what happened? Well, what happened was I had that register, and I put that into register 4. I had my byte down here, 0xFD, and I loaded that, right? But what happened to the other 3 bytes here? Well, it padded those with zeros. So ultimately what I really had was 0, 0, dot, 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 0, and then the FD, which will have the bit pattern 1, 1, 1, 1, 1, 1, 0, 1. Well, the thing is that this right here is not a negative number in 2's complement. The sign bit is down here. When I'm looking at it in terms of only 8 bits, 1, 1, 1, 1, 1, 1, 0, 1, there's the sign bit which says it's a negative number if I'm thinking of this as being a 2's complement representation of a negative number. If I thought of this bit pattern as being unsigned, it could potentially be, or would actually be, a non-negative number. But I'm thinking about this as being -3, and that's my interpretation. All right. The problem is once I copy it up, it pads with these zeros, and now I've produced a positive number, and I added that positive number to 20 and got something else. So what we really need to do is take this 8-bit representation of -3 and write it to R4 in such a way that I get the 32-bit version of -3, which is this right here. And for that, I'm going to use the idea of sign extension. So what's going to happen is it's going to take this smaller value, so it could be for bytes, half bytes, whatever, as long as it's smaller. It's going to take the sign bit and it's going to replicate it. So I would have whatever that sign bit is, and then what remains. And so to do that, now for my load, I still will have the B to indicate it's for a byte, and if it was a half byte, it'd be an H. Well, I'm going to add the S here. Now what happens if I had a number that I thought had been positive before, so the sign bit was a 0? Well, that's fine, it just replicates that with zeros. And in fact, that's what happened with the 20. That's the reason why I didn't actually extend it with the 20 and add zeros. It's just that because it defaults to padding with zeros, it got the same result. So now what we need to do is do it in such a way that we get the correct value. So now I'm going to take this code right here, and let's finish this. And now let's change this to S. And we don't actually need this now. There's my 20. Now notice, in addition to the lower byte, which was FD, I got all these Fs, and now when I add, I get my 17. And then we could just continue and quit. So once again, this is sign extension, and I was using it for bytes. If those values had been half words instead, so if this had been, half word in the GNU assembler directive, then I would have used an H right here and read that in. Now, if we're talking about saving values from a 32-bit register into, say, only 8 bits, then I just use something like this. strB or strH, and you get the lower byte of what's in the register, or the lower 2 bytes of what's in the register. The idea of sign extension doesn't apply here because we're going from something that's bigger down to something that's smaller.